Well, should I keep speaking English or? I think for you it's better in English. Yeah, okay. Well, let me first write down without any, before we proceed to some homogenization problem, let me first introduce non-local operator of convolution type. You know, pure convolution type, and everybody in this audience know what pure convolution operator is. But when we say convolution type, we mean the following operator. It's integral over, let's say, RD, where in the whole space. Bounded domains are also possible, but for non-local operator, bounding the condition is a tricky issue, so I prefer not to discuss too many topics simultaneously. So let us at least start with the case of the whole space. So it's this. Then there is a convolution kernel, x minus y, and I write down so the operator u of y minus u of x dy. That's our operator. Now that's the function on which it acts. We usually assume that u is an element of L2 of RD. A is mu is a coefficient which is responsible for local characteristics of the media. Because if we remove this mu, if we assume that mu is equal to 1 or any constant, it will be pure convolution operator. And then the localization property of this operator, how close in a sense it to local operator, depends on the localization property of this kernel. While this term and this term are parts like in the case of, let's say, partial differential equation. Without this term, it would be the analogy to operator with constant coefficient. If we want to have non-constant coefficient, we have this coefficient mu, which is responsible for the local characteristic of the media, and it depends, in contrast with partial differential equation, it depends on two variables. Because the operator is non-local, for jump process there is starting point, there is end point, so there are 2 points here. In analytical terms, okay, you in this expression, u is evaluated at point y and point x, so the coefficient should also depend both on x and y. Then later on we will impose some coefficient, some assumption on this mu, like in homogenization of partial differential equation. We cannot homogenize arbitrary operator with arbitrary coefficient. It doesn't make sense. Usually we assume some form of translation invariance. It might be periodicity, quasi-periodicity, almost periodicity, then it's more strong form of periodicity is the strongest form of translation invariance. Almost periodicity is still close to this, and we can assume that it's random stationary, then it's translation invariance only in terms of distribution, but still in all these cases there are very nice results in homogenization theory for partial differential equations, for elliptic, for parabolic, even for hyperbolic. There are many nice results. This theory started about 50, maybe 55 years ago, and at present homogenization of partial differential equation is very well understood topic where there are many nice results, many techniques. We try to borrow some methods and some approaches from this theory. It worked, but not directly. In many cases, if we wanted to borrow some approach from partial differential equation, the fact that we have operator non-local, this fact required that we modify essentially this approach. Directly, it didn't work. So, what do we assume about the coefficient A and mu? let's start with A. We assume that A is okay. We want to have something similar to elliptic operator. We need positiveness. As you know, if we, for PDE, for example, if we assume that coefficient can change sign, doesn't possess any ellipticity assumption, then we can say nothing. Similar thing here. If we assume, if we do not impose some coercionist condition or some condition under which this operator is bounded in certain functional framework, then we will be lost. So what do we assume? First condition. First condition is on A. A of Z is non-negative. Second condition. A is integrable, which is equivalent under this condition to say that it's L1 function. Z less than infinity and greater than 0. We want to exclude trivial case when operator is just 0 operator. And the third condition is the condition that the second moment of this coefficient A is finite. And it's a very important condition.
Well, 3 implies 2, yes?
Sorry?
Condition 3 implies condition 2, I guess.
No,
Oh.
no, not at all.
Okay, maybe some singularity is
It might have singularity at 0. For instance, we can assume that there is, like Levy type operator, if we cut the tails, this condition will be satisfied, but this condition doesn't hold. Well, the three conditions we impose on A, and these two conditions are kind of positiveness condition and boundness in fact, well, I will comment on this later on. And this condition is very important because if you think about central limit theorem, you can easily assume that second moment should be finite, otherwise there is no hope to have in the limit something of diffusive type. Here's the same picture. If we do not impose this condition but impose some weaker condition, then there is no, still in some cases homogenization is still possible, but diffusive scaling in case of parabolic problem, diffusing scaling doesn't work anymore. We need some different scaling adapted to the moment we have. And some, with respect to this moment, some uniformity is occurring, otherwise we can have nothing in the limit. So the most natural case and the case which is very stable from the point of view of the limit behavior and of the type of scaling we impose is the assumption that we have just finite second. Now mu. Mu, we want to have uniform ellipticity, so we impose the standard uniform ellipticity on mu. Condition 4. Uniform ellipticity. We assume that there are two positive constants, mu minus and mu plus, such that mu of xy is greater or equal than mu minus and less or equal than mu plus. Classical uniform ellipticity condition. And in our first, let's say, in the first problem we're going to study, we assume that coefficients are symmetric. In fact, later on we will drop this condition, and the price to pay will be homogenization and moving coordinates. But let us begin with symmetric case. So condition 5, symmetry. That the condition which mu is 0, 1 to power d periodic. in the variables x and y. This means that it's periodic in each coordinate direction with period 1. And a is even function. A of minus az is equal to a of minus z. Since in the kernel of the operator there are, the kernel consists of two functions, we need symmetry condition for both of them. Symmetry condition for mu is given by, oh no, sorry, I mixed two different conditions. Oops.
Mu minus.
Periodic and this.
Zero. Mu minus. Oh, you allow.
Mu minus. Oh no. It's a mistake. It should be. I don't want to consider. Okay. Now there are some works on the generate equation, but there are many additional assumptions. So I prefer to assume here that. That the inequality is strict. Thank you. Well, and the last condition is the condition that operator is symmetry. It's not here. Sorry, I mixed two different conditions. It's periodicity. It's periodicity. Periodicity. That's the periodicity condition. On A, we do not impose it. A is the localizing part of the kernel, so we do not assume any periodicity, of course. It's integrable function. Mu is periodic. And the last condition is symmetry. And symmetry condition consists of two parts, condition on mu and condition on A. So on A, it's A of minus z is equal to A of z. For any z from Rd, it's even function. And mu of x y is equal to mu of yx, usual symmetry for mu. So we have this framework. And what can we say about this operator? This operator is always a bounded operator in L2. That makes a big difference with differential operator. So let's go further here. So lemma, simple lemma. A is bounded in L2 of Rd. Well, let me explain why. So we have, let me remind you that AU of x is equal to integral. Let me, we have two parts, u of y minus u of x. Let me write it separately. It's a of x minus y mu of xy u of y dy minus integral a of x minus y mu of x y dy times u of x. Do you agree? U of x, we can send it out of the integral. So this function, what we can say about this function? Integral of x minus y dy is a constant. Some constant, without loss of generality, we can assume that it is 1. Just redefining a and mu, we can assume that the integral of a is equal to 1. And mu lives between two positive constants, so this coefficient also a function of x, which stays between mu minus and mu plus. So the second operator is multiplication of u by some bounded positive function. Of course, this operator is bounded in L2. What about this one? If A is, maybe I should write that it's integral over RD. Here we use the famous Lemma-Schur test, which says that if there is a kernel, and if we have integral arbitrary operator with kernel k of xy, u of y, rd, not necessarily rd, but I will apply it to operators in RD. And if it's Schur, usually the theorem is called Schur test. I don't know why. If integral of k of x, y, dy, let's write modulo, supremum in x less than infinity, and integral of modulo k of x, y, dx supremum in y is less than infinity, if these two conditions are satisfied, then this operator is bounded operator from L2 to L2. In fact, this Schur theorem covers much wider framework, but for my purpose it's sufficient to formulate just particular case of Schur theorem. And you see, very nice, since if we integrate it in x and in y, it doesn't matter, we immediately see that these expressions are less than infinity, so this operator is bounded operator in L2. So we have the difference to bounded operator, it's a bounded operator in L2. Yes. So first, big difference with partial differential equation. We have a familiar bounded operator. Then, let's go further. What else can we say? We also, in the symmetric case, we assume, for a while, we impose the symmetry condition. We can easily check that this operator is non-negative. It's bounded on L2 and it's non-negative. So what we can easily check that A, U in the product. If in the product in L2, I will not write down the index L2. By default, the in the product is in the product in L2 of RD. That is equal to integral over RD, integral over RD, A of x minus y, mu of x, y, u of x minus u of y, square dx dy. And this implies immediately that this operator is non-positive, and in fact it's positive but not uniformly. It's it's negative but not uniformly, and this means that minus a is positive. And as a consequence of this, if we consider an equation, au minus u is equal to f in L2 of RD, then the problem is coercive, and there is a unique solution because of this, just directly by, I don't know, Rees theorem, if you want. By this coarseness as operator, we immediately have that there is a solution, there is a unique solution. This equation has a unique solution. solution. And then easy estimate both the norm of u in L2 is less or equal than the norm of f in L2. With coefficient 1, because we have coefficient 1 here. So very nice properties of this operator. Now, we can also consider the evolution version of this equation, because we think about at the end we are going to consider the parabolic operator, and in fact many results can be formulated only in for parabolic version of this equation. We want to consider also the parabolic version. So if we consider the operator dtu is equal to AU, let's say Cauchy problem, u t equal to 0 is equal to some given function u0 from L2 for d. Then since it's a bounded operator, the semigroup converges. The semigroup is very well defined, and we have that u is, the operator is non-positive, so it's a contraction semigroup. We can solve this equation. There is a unique solution, and u of x t norm is less or equal in L2 is less or equal than the norm u0 in L2. That's what we have. Now homogenization. So far we dealt with just operator for fixed x. And as I told you already, in order to do homogenization, we need some form of translation invariance. And today I will assume that in spatial variables we have periodicity, the strongest form of translation invariance. In fact, the problem with the problem with statistically homogeneous coefficient was also solved. And I didn't tell you that the result I'm presenting today is our joint work with Елена Жижина. Let me write it here, Елена Жижина. Well, also in variational framework we did this together with Andrea Braitis, but today I will not touch this. So maybe I write also variational problem of this type. With Andrea Braitis. So with Елена Жижина we studied.
No,
We studied the both periodic case and random statistically homogeneous case, periodic case, symmetric and non-symmetric. All these results were obtained in collaboration with Елена Жижина. Well, so we have this problem, and now we turn to homogenization. And before discussing homogenization, let me say a couple of words about the probabilistic meaning of this operator. In fact, this operator, pure convolution operator, everybody I think knows here that it's a generator of jump process. The process stay at a given point for exponential time, and then make a jump, and the distribution of jump is exactly this A. And then it's this process with the independent increments. But if we have this additional coefficient mu, then it's a generator of Markov process, not with independent increments anymore, Markov process, and the intensity of jumps is given by normalized by the expression here. So this product is gives just as the intensity of jumps from point X to point Y. And it's well known, it's one of the classical process in jump Markov process, purely jump Markov process in RT, so process stays for financial time, they make the jump, and intensity is given by this expression. So, and it's well known, at least if mu is equal to 1, then it's well known that under the condition that the second moment is finite, this jump process satisfies the central limit theorem. So we expect diffusive behavior in the limit. So it means that it is natural to assume that just some argument kind of waving hands, but in fact quite deep arguments why we should impose diffusive scaling for parabolic equation. Why if we scale x with a small parameter epsilon, time should be scaled with small parameter epsilon square, diffusive scaling. So what we do, we introduce a small parameter epsilon. Epsilon greater than 0 is a small parameter. Small parameter. And we do scaling. We want to homogenize the process. We want to study a big frame of our media after large time. And in order to make everything of order 1, we scale this, we take the typical size of homogeneity. We consider the ratio between the typical size of homogeneity and the size of the whole pattern or reservoir, what it depends on the physical or biological nature of the problem, of the whole domain. And this ratio we denoted by epsilon is a small parameter. And in mathematical language we send epsilon to 0. Well, and so epsilon x t epsilon square t. It's diffusive, standard diffusive scaling. And we check what happens to our operator under this scaling. Our parabolic equation, you know, for instance, that the standard heat equation is just invariant under the scaling. If we do the scaling, heat equation remains unchanged. Here we will have the following picture. After this scaling, I drop the details, but it's just quite simple exercise to check that after this scaling, we will arrive at the following equation. dt u is equal to 1 over epsilon to power d plus 2 integral over rd a of x minus y over epsilon mu of x over epsilon y over epsilon u of y minus u of x dy. You can ask, why do we have this strange power of epsilon? Well, 2 is coming from scaling of time. Epsilon square appears in front of time, we divide by it. And d is just Jacobian. When we change in d-dimensional space, when we replace dy with a d epsilon y, we obtain 1 over epsilon to power d. So d is coming from the Jacobian, and 2 is coming from the scaling of time. So that's our U operator. It's bounded for each fixed epsilon, but its norm is getting bigger and bigger because we have a large parameter in front of the operator. So now we know that for each epsilon there is a solution. This solution still satisfies this condition because of course, I consider the same Cauchy problem, but instead of A, I use operator A epsilon. Now. And usual question and homogenization problem.
Do not scale initial function. Initial function is not scaled.
Sorry?
U0 is not scaled. U0.
U0 is fixed.
Fixed.
It's fixed, like usually in homogenization theory. The right hand side is fixed, the parameter in the operator goes to 0. So Because if we also scale U0, we'll obtain 0 in the
sure.
limit. No, so it's tricky. We keep the initial shape of U0 unchanged, while the parameter in the operator tends to 0. That's why it's not equivalent to the central limit theorem. It's a weaker form of the central limit theorem because we keep the initial function unchanged. We do not scale it together with the operator. Well, and the question, what's happened to U epsilon as epsilon goes to 0. And now I formulate a theorem. The people who are familiar with Markov process can guess that in the limit we should have diffusion operator. Since period is getting smaller and smaller, and of course the limit operator should inherit the translation invariant property of A epsilon, the limit operator should have constant coefficient. And that's the case. So theorem. U epsilon converge for any U0. Let me write it. For any U0 from L2, U epsilon converge to the function U, let me write 0. I hope you will not mix lower index 0 and upper index 0. XT. Just okay, it's not correct to write this way, but so U epsilon converge to U0 in the space C0T with values in L2 of RD. So the supremum norm in time and L2 norm.
In L2 uniformly over T.
And where U0 is the solution of the following problem, where U0 solves the problem, the Cauchy problem, dTu is equal to divergence A effective gradient effective gradient U t equal to 0 is equal to U0, and A effective is a constant positive definite matrix. Constant positive definite matrix. So what we have that the solution of this problem with this operator, which is non-local, in the limit converge to the solution of local operator.
L2 is equipped with a strong topology or the weak topology?
Strong topology. In fact, we can even show the convergence in the operator topology. The result is the convergence is very good here.
We'll write the formula for effective formula.
Yeah, formula for the effective coefficient. I'm going to write it down now. I'm afraid I don't have time to explain the tricks to comparing to the PD. What we, okay, you know, now in homogenization theory for PD, there are several very efficient methods. But the most intuitive method is the method of asymptotic expansion. Two-scale convergence method works better for wider class of problem, but it's not intuitive. You do just permanently do some functional analysis, and often you don't see why. You have some result, you don't see why. So I prefer to explain here in terms of the asymptotic expansion, one of the oldest methods, asymptotic expansion technique. Why? What we're doing here? It can be after that translated to other languages, the language of two-scale convergence. Several methods can be used here. But what we do, we take the solution of the limit equation, we take the initial data nice enough, we have uniform a priori estimates, so it's sufficient to prove the theorem for the dense set. We take the Schwarz class function for the initial condition, then solution of the limit problem is a Schwarz class function for each time and regular in time.
Do you understand right that the drift is absent because of the symmetry, yeah? Because of the symmetry.
No drift because of the symmetry. In non-symmetric case, we will see there will be drift, yeah. What we do, we say that we try to approximate the solution of original epsilon problem using some ansatz which is constructed in terms of the solution of the limit problem. That's the idea. So we write that we expect that the limit is u0 of xt. So we write it. But then, of course, we should correct it somehow. We should write an ansatz, we should write higher order terms in a clever way, in such a way that after substitution to the original equation, the right-hand side becomes small because we have 0 is right-hand side. In fact, it's not necessary to have 0 on the right-hand side. We can also have some right-hand side. It's just easier to explain the method with initial condition only. Method also works for non-trivial right-hand side. So we write plus epsilon, and then what happens that we can write this, where this chi is a periodic function of its argument constructed in a clever way. Plus epsilon square, let's say theta of x over epsilon, nabla u0, and well, that's sufficient. In fact, even two terms would be sufficient. These terms only required to write down formally the compatibility condition. So what we do after that, the same trick is used in PD, but in PD, when we substitute this in the epsilon equation and collect power-like terms with respect to epsilon, we have the equation of the following form: some differential expression for chi multiplied by this function evaluated as a poise xt. And then we say, since this, the idea is treat x over epsilon and xt as independent variables. Since epsilon is changing, we treat x over epsilon and xt as independent variable. Then there is a common factor nabla u0 of xt, and the expression we want to be 0. It's this power-like term of order epsilon to power minus 1. Since there is nothing on the right-hand side of order epsilon to power minus 1, it should vanish. So in order to make it vanish, we obtain equation for chi. And this will be the common factor. Here it's not the case anymore. Why? Because we evaluate this difference at two different points. And we will have u0, for instance, of xt, and u0 in the other expression of yt. And it seems that the method is ruined by this. It doesn't work. But the idea is that because of the very strong localization, you remember, maybe we have this A, which is more and more close to the kernel of delta function, yeah, with appropriate factor. So it's localized more and more. The contribution of these two functions is due to the x and y which are very close to each other. Otherwise, a of x minus y over epsilon is getting negligible, because you remember second moment is finite, so it's really localized. This gives us the idea that we should write, the trick is, we write y as x plus epsilon x y minus x divided by epsilon. Now this term is consistent with the argument of the function a. Everything is typical change of the function happens in this scale, and we have a small parameter, and we can use Taylor expansion for this. And making this Taylor expansion, we obtain some additional terms, but all of them will be evaluated at the point xt. Y disappears, and that allows us to write down the equation for chi, because now they have common factor, some function on u0 or its derivative, and we want the coefficient in front of them to become 0 when we collect terms of order epsilon to power minus 1 and terms of order 1. Low order terms doesn't matter because they go to 0. That's good for us. That's the idea how it is done. I skip it. Of course, it's a lot of computation. Quite straightforward, but still. I write down the equation for chi. Chi is periodic function, so now we live on the top. Original operator is given in RD, but now since chi should be periodic, we have a problem on the torus. This problem reads: integral over RD a of x minus y mu of x y chi of y minus chi of x minus x minus y dy is equal to 0. You see there is a non-trivial right hand side. When we integrate x minus y, integral over RD. Nevertheless, it's easy to check that the result of this action of this operator on this difference and on this function, all these results gives us a periodic functions. It's a simple exercise. For instance, for young people, it's a good exercise to check that indeed this operator x from L2 on the torus to L2 on the torus. I mean, without this additional term. And with this, if we integrate this difference, it's also a periodic function.
But here it is just the symmetry of a
Not
x
even
minus y.
symmetry. Look, if we let's say add integer vector to x.
It is a single integral or double integral?
It's single integral. It's single integral.
Okay.
It's equation, so it should be satisfied point y
There
and
is
x.
no x minus y. This is the variance measure of this jump process, okay?
Sorry?
If you delete this term x minus y, we're looking for a variance measure of...
If I delete this, then chi
which is obviously
unique
periodic.
solution is a constant. Because you remember, I wrote you that this integral is non-positive.
Yeah.
And on the torus, it has unique eigenfunction, simple eigenvalue 0, and unique eigenfunction constant 1, for example. Yeah. And because again of this formula, quadratic formula, there are no other eigenvalues. As soon as there is oscillation, the value of integral will be quadratic form will be positive, so the eigenvalue is simple. Operator symmetric, so adjoint operator also has. And why? Let's check. So, but this equation has a non-trivial eigenvalue, so we should use some kind of Fredholm theorem. Compatibility condition is not for free, we should check it. But what do we have? This operator is multiplication by a function which is bounded by a positive constant from below and from above. So this operator, when we multiply chi of x by this function integrated in y, it's invertible operator in L2, and this operator is compact. It's operator on the torus. Well, if A is L2 function, then it's trivially compact. In fact, it's not complicated lemma to prove that even for function from L1, this operator is still compact on the torus. Let me skip it. Places just some technical approximations. So we have the sum of invertible operator and compact operator. Then Fredholm theorem is symmetric. So Fredholm theorem perfectly works. And compatibility condition is just orthogonality of the right hand side to constants, because in the kernel we have constants. But look, this guy is symmetric, this guy is symmetric, this guy is antisymmetric. So there is a solution. We construct our chi, we substitute it in the equation, we kill all the terms of the epsilon to power minus 1, and then standard machinery works and we obtain homogenization result. I prefer to skip this part because I just follow the strategy which was elaborated 40 years ago for partial differential equations. Okay, so we have the result with this corrector, we have the result for symmetric operators. So in the limit, we have just heat equation up to some linear change of variables. And we have interesting fact that in contrast with homogenization theory for differential operator, here we start with the family of bounded operator, and in the homogenization limit, we have unbounded operator, PD. Well, what happens if we drop the symmetry condition? We keep the condition on periodicity and positiveness of the condition except for symmetry. So we drop symmetry condition. Let me write it down that we now consider non-symmetric case.
But also you promised the formula for effective.
Formula, да, formula is the following. Formula A effective. Is equal to integral, double integral, this one over RD, this one over D. This one over the whole space, it's over of the period. A of x minus y mu of x y, and here we have, let me write it like this, A psi. I write down the x of matrix A on quadratic form with some vector psi from RD. And here we have 1/2 psi minus psi chi of x minus chi of y dx dy. Sorry, I don't know.
And how you know it's positive? Because high
Yeah, and then it's very interesting exercise to check that it's positive definite. Using the equation for chi, we can rearrange this equation in such a way that it's getting a positive quadratic form due to the equation. So originally we obtained it in this form, but then using the equation, you see that it's piece of equation. So making this using the equation and substituting, inserting one part of equation for another part of equation, we finally obtain a really positive quadratic form for it. That's how it works. So, of course, it was checked. It was an important part of the business to check that this matrix is positive definite. It is. So you see, it's matrix, it's scalar function, and at the end we have quadratic form with some matrix which is denoted by A effective. It's positive definite. It's a positive definite matrix. And symmetric. Of course, if not, we would symmetrize, but in fact, it's symmetric from the very beginning. With the definition, it's also symmetric. It can also be checked. Well, that's the formula. And it's coming from, for example, from this asymptotic expansion. When we collect the terms for the zero, compatibility condition gives us this, exactly this. You remember, since we're on the spectrum, we need orthogonality to the constants. We check it, and this orthogonality condition gives us the. And with this orthogonality condition, we kill the terms for the zero, and this means that we approximate very well the solution of the original epsilon problem. And then we use a priori estimates, and we're done.
And the unique information that I have about psi is the equation that you wrote previously. Not psi, chi. Chi.
Yeah, chi is the equation which exactly is the equation which was written previously, yeah. Chi, so we collect terms for the epsilon to power minus 1, we obtain this equation for chi. And then we collect the terms for the zero. We will also want to make it zero. And when we do this, there is formally, we write down the equation for this guy and check compatibility conditions for this. When we do it, we obtain that this.
And you have also some variational formula for this.
We can use gamma convergence approach. It also works, yeah. And of course, it gives the same formula, yeah. As usually in the periodic case, the minimizing over big pattern is reduced to minimizing over one period, and it's in fact the corresponding earlier equation for this minimization problem will be exactly the problem for chi which was original. That's well. Now, non-symmetric case.
I think there's a problem with blackboard. Maybe.
With the boot? Maybe
Yeah,
right here, yeah?
Here it will be better.
Yeah. So we don't assume anymore that A is even, neither mu of xy is equal to mu of yx. We drop both conditions. In fact, it's sufficient to drop one of them, but now as soon as at least one of them is not fulfilled, then we cannot use symmetry anymore. So then we expect the law of large number. And now the question, how to express in analytic terms, in terms of homogenization, simultaneously. So far what we did, it was a weak form of the central limit theorem, diffusion in the limit. But how to combine in one limit theorem both the law of large number and the central limit theorem? Because now we expect that, since no symmetry, we expect some non-trivial drift in some direction. And so in the non-symmetric case, we try to play the same game. We write down again. Since we expect diffusion in the limit, we take the limit equation, which is diffusive. We take nice initial data. We obtain the nice solution, which is Schwarz function everywhere, infinitely many times differentiable in time. But if we do all this business, if we write that u epsilon is equal to u0 of xt plus epsilon chi of x over epsilon gradient u0 of xt plus and so on, and if we substitute in the equation, we will obtain the same equation as before, because in the derivation of the equation we didn't use symmetry at all, over Rd a of x minus y mu of x y chi of y minus chi of x dy is equal to the integral over Rd x minus y a of x minus y mu of xy dy. I just sent this term on the right hand side at the same equation. But now this term is not symmetric anymore, and on top of it, it should be now, the right hand side should be orthogonal to the kernel of adjoint operator. And the kernel of the adjoint operator is not a constant anymore. That's the problem. So we face two problems. First, that the compatibility condition required the kernel of the adjoint operator. Well, even we cannot use anymore also as before, we could easily check that the operator is non-positive. Here it's non-self-adjoint operator, so we can also say, or we can only say that it's accretive operator. In fact, this operator, the essential part of our work for non-self-adjoint case was studying this operator. What we can show using some non-symmetric Fredholm theorem and also some special branches of this Crane-Rootman theorem, because we use positiveness of the coefficient. So what we were able to prove? Theorem. If we denote this operator, this one, by a periodic chi, now it acts on the torus, so I prefer to use another name with hash, which means that the operator acting on the torus, on periodic function. So, theorem, the kernel of a hash star is one-dimensional and doesn't change sign. So under the normalization P of x satisfies this condition P plus P minus. Under the normalization, the integral of P of x dx over the torus is equal to 1.
Suppose that mu is constant, but A is not symmetric. Can this be proved without having machinery?
But if A is mu is a constant, then a joint operator has the eigenfunction is also 1.
Yeah,
So it's trivial.
easy.
But if mu is not a constant, then the kernel of a joint operator is not constant anymore. But what is important for us, that it's a function which is bounded and which is uniformly positive. Of course, under the appropriate normalization. That's the first thing. And for the additional operator, we have also so by Fedgold's theorem, then we can say that this equation has a solution if and only if the function here, function of x, is orthogonal to P of x. And in general, it's not the case. It is not orthogonal. Why? No reason for this. So it's easy to check that in fact this condition. So Fredholm theorem works. Kernel is one-dimensional. Kernel is very nice, but still compatibility condition is not satisfied. And it seems that we are trapped, but in fact we are not. Why? Because we expect the law of large number. We expect non-trivial speed. And we didn't introduce it so far. Of course, we should face the problem because until now we didn't take into account the drift. So what we do? We say that we will evaluate when we construct U epsilon, we will evaluate for, the function U0, not at the point xt, but at the point x minus b bar over epsilon t. We take limit function and we substitute the x shifted with a constant vector for the 1 over epsilon. So far unknown plus epsilon chi of x over epsilon, gradient u0 again. And we substitute this in there. When we do this Taylor formula in x and all this thing, nothing changes. Just the argument we replace everywhere, the old argument with this one. But when we differentiate in time, in front of gradient of 0, we obtain additional term 1 over epsilon b bar, gradient u0, when we differentiate in time, just by chain rule.
If mu is constant, this could be split elementary, I guess.
Yeah.
Just in this simple case, could you just explain it on the very elementary level of what is going on? Suppose still we have this b bar, right? If I is not symmetric, but mu constant, it should be elementary fact.
If mu is not a constant. Well, in fact, the computation I do here, it will be directed. Just this term will not be required. But we play the same game here. We substitute without this term, and we will see what b bar is. You will see it right now. So we substitute, and what we have again for the same equation, collecting terms of epsilon to the power minus 1. We have only one additional term coming from derivative of this guy in time, which is 1 over epsilon, gradient u0, b bar over epsilon, right? Differentiate. There are two. Derivative in time gives us two terms. One is the standard, just the derivative of u0 in time when we treat the second argument, but when we treat the first one, there will be b bar over epsilon, number u0. This one, right? the full derivative in time is this term plus dt u0 of, okay, with the same argument.
And minus. Minus.
Yeah. And this gives us extra term for the 1 over epsilon. So in our equation here we have plus b bar. And now we want to choose b bar in such a way that for the new equation compatibility condition is satisfied. And of course it means that we should multiply this by p of x and integrate. B bar multiplied by p of x and integrated, it's again b bar, because integral of p. And we obtain nice formula for b bar. So we obtain analytic expression for the velocity in the law of large number, which reads b bar is equal to integral of x minus y mu of x y a of x minus y p of x dy dx. If
One over towards integration.
sorry,
Integration over
yeah, double integration.
double integration. One over
Over RD and over
another over torus, yeah?
RD and TD. Look, in the case when mu is a constant, this guy disappears, this guy disappears, and it's just first moment
Yeah.
of A. Trivial. So that's the answer to your question. In the case of trivial mu, constant mu is just first moment of A. Well, and we obtain, and as soon as we take into account this guy, we make this equation solvable, we use the same machinery as before, and we obtain very nice result, but in moving frame, because now we should evaluate everything in the moving
But
coordinates.
you will get some effective diffusion coefficient which will be different from the symmetric case.
Yeah,
Right?
Yeah.
Do you have some inequality between them or not? I mean, if you compare, you consider A, which is, for example,
Okay.
A
A
asymmetric
mu
and
and
asymmetric.
how can we compare symmetric and non-symmetric functions?
But
That's the question.
take-
We have function of two arguments.
No, but I take A, which doesn't have any symmetry property, but I consider the symmetric A, the symmetric part of A.
Symmetric part of it. You mean what happens if we symmetrize the...
Yes.
I don't, the answer, I don't know.
No, because
didn't check.
I know that in some cases there are some comparison in the interacting particle systems.
Maybe, good question.
Pair.
We just didn't check. So you mean let's symmetrize and compare, then we can use symmetric case.
Usually we
can
expect that
compare
it is
diffusion.
bigger for the asymmetric case than for the symmetric case.
I would expect so, but since we didn't check
But you have still some variational formula for the.
for symmetric case, we have variational formula.
But for the asymmetric case, you don't have some variational formula for the A, the effective A.
For non-symmetric case?
Yes.
No,
No.
no. Well, so let me formulate the final theorem in this case. The theorem reads that under all the above conditions, from 1 to 5, without symmetry condition, we have the following statement. That the integral supremum in time, for any time, t capital is arbitrary number. Less or equal, integral u epsilon of xt minus u0 of x minus b bar over epsilon t square dx tends to 0 as epsilon goes to 0. So we have convergence, what we call in moving coordinates in a moving frame, because the limit function is evaluated not in the coordinate xt, but in the linearly moving. The frame is moving linearly, but speed is getting higher and higher. That's what we expect by the law of large number. Well, and now we switch. I still have maybe 10 minutes, yeah? I think I should write on this part. So now we have mu of x, y, t, and we assume that mu of x, y, t is periodic in x and y and stationary ergodic in time. Ergodicity, even ergodicity condition can be dropped, but then the answer is quite ugly. So I prefer ergodic case.
Well, maybe the product of function of x of
Yeah.
some random function of
Yeah.
t. Yeah?
So periodic, as before, 0, 1 periodic in each coordinate direction in the variables x and y. Stationary ergodic in time. The rest is the same. A is not necessarily symmetric. A is the function which has a finite second moment, non-negative. Conditions from 1 to 5 are fulfilled. Symmetry is not supposed, and we assume that dependence on x, y, and t follows this follows what is written here. Now, if we do play the same game, then we arrive at very interesting parabolic auxiliary problems for chi. If we try to write down the ansatz, the equations. Now time is involved. We consider the operator dt. Let me write down what we are studying, what equation we study, equal to 1 over epsilon to power d plus 2, integral over rd, a of x minus y over epsilon, mu of x over epsilon, y over y over epsilon, t over epsilon square, diffusive scaling, u of y t minus u of xt dy, and some initial condition u t is equal to 0 is equal to u 0. The same problem, but now there is equation is non-autonomous, there is non-trivial dependence on time. And if we play the same game, I repeat it again and again, if we play the same game with asymptotic expansion, we arrive at the following interesting problem for chi. Chi should satisfy the equation ds chi. Now chi is time dependent of x s is equal to the integral, let me write it like this, of s, because now operator depends on s, which is equal to integral over rk, a of x minus y, mu of x, y, s. Sorry, I forgot chi here. Chi. 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 S minus chi of x s g y. That's auxiliary problem on the torus multiplied by real line. So what should we impose, what condition should we impose on time? Of course, there are many solutions, because we can consider any Cauchy data and solve this equation. This equation has many solutions. But we are interested in a stationary in time solution. What is important here, since we scale time more and more, we are not allowed to impose any Cauchy data, because very soon this Cauchy data will be inside our interval. So we should have stationary solution. So the question is, do we have a stationary solution of this equation? And the answer is yes. There is a unique stationary, quite non-trivial theorem, says that this equation has a unique, of course, up to a multiplicative, up to a multiplicative constant, which might be random, unique up to multiplicative solution, stationary solution.
Now we do not assume any symmetry of A and mu, right?
Sorry?
So now we do not assume any symmetry.
No, no symmetry. No symmetry. Stationary solution. That's one thing. And second thing, kind of weak form of Fredholm theorem. The operator is not Fredholm at all, nothing in Fredholm. Nevertheless, there is very important property, that equation. That was the first part. The second part, the equation. If, let's consider here, let me write down the equation here, dt. V is equal to, V is a periodic function on the torus, is equal to A hash of t V plus some function g of x t, which is stationary. So, second part, if the integral of g of x t chi is not a good sorry solution. No, here I said stupidity, because here of course it's a constant. I mean a joint operator here, sorry. Let me, I started to hurry up and made a mistake. So let me write it like this. We studied not this operator, but let me change the name just to be consistent. And here we have star P star P.
And P under the integral as well, yeah?
P. And here, of course, we have, it's not correct anymore. We should take the joint operator. I wrote it down already. Let me skip this. For x, we keep this form, but for y, we change the order. We write y minus x. Okay, let me, maybe I should write it at least once. I want to remove this part. Let me write it down, because it's a joint operator. sorry, it's a joint operator, and this joint operator is integral of A over Rd, A of x minus y, mu of xy, dy, p of xt, minus, with minus, and here plus, integral over Rd, A of y minus x, mu of yx, the joint operator, integral operator, we should change the order. P of y t dy. So we consider this equation. And this equation has a unique stationary solution, which is P of xt, which has a name for it. Normalized, let's say, in such a way that the integral, we can show that the integral over the torus doesn't depend on time due to the equation. And we normalize it by the normalization condition that integral for each time integral of the torus is equal to 1, because it's defined up to a multiplicative constant.
Sorry, could you repeat what is that equation? The right on V.
And this equation we want to solve it. It's on the torus. We are looking for a stationary solution given stationary function g. We ask the question if there is a stationary solution on x on the torus, if there is a stationary solution of this equation. The answer in this given this, by the way, what is also will be useful for us is that this solution has very nice property in the sense that it stays between two positive constants. Second, P of xt is less or equal than P plus and greater or equal than P minus, which is strictly greater than 0. So this stationary solution satisfies uniform, almost surely satisfies uniform estimates from below and from above. And the third property, that this equation, let me give it the name star, if integral of g of xt, p of xt, dx is equal to 0, almost surely, for each t, then star has a unique stationary solution, has a unique up to an additive constant.
Let us assume that mu is split at the product of two functions, function of s and y and function of t. Is it true or not that j can be split or not? Suppose mu is split. The product,
yeah, of course.
Should be also split.
Of course, in this case, yeah, we solve elliptical equations and
separate variable.
Yeah. But if not, then it's
okay.
Unique solution. Well, and combining all this property, do the same business as before, and in the case non-autonomous equation, combine this property, we arrive at the following theorem. 1 minute. There is a random process. There is a stationary process. Let's call it G of G of t such that integral of u0 of x minus 1 over epsilon integral from 0 to t g of s over epsilon square ts t minus u epsilon of xt square dx supremum in t between t capital and 0, that goes to 0, s epsilon goes to 0. The question, what is this stationary process G? This stationary process G is in fact just integral of G of t is equal to integral of x minus y, a of x minus y, mu of x, y, t. P of x, t, dy, dx. We formally write the compatibility condition, and then we use the theorem which was used to resolve the equation for chi. And this sufficient condition for existence of solution uses this. In order to make this equation solvable, we should subtract the integral which is here. Then the condition is satisfied and there is a stationary solution. And that's the function of t, and we just use it. Now you see the moving coordinates are rather non-trivial. We have very nice convergence to the nice profile, which is the heat kernel profile, but in non-trivially moving coordinates. It seems that we cannot say more, but in fact we can. If we have good mixing property, then what we can say, that this part can be decomposed in the mean value, which gives us the movement as with the constant speed as before, plus the expression, if good mixing property are satisfied, it's certain work, technical work to do, but we can show that in this case, the convergence to the invariance principle holds, and in the limit we will have just Brownian motion. So this guy can be represented as B bar, 1 over epsilon, B bar, plus W T, some sigma WT with constant sigma winner, d-dimensional winner process plus O small, little o of 1. Well, and then if we substitute and use eta formula, we will see that it will be a solution of stochastic PD with finite dimensional multiplicative noise. So in the case of good mixing property, we have very nice theorem that original solution converging law in the space in which we have convergence to the solution of stochastic PDE with multiplicative finite dimensional noise. That's the last result I wanted to present. Thank you.
Just make one remark. What a reasonable referee should write to you, as I understand it. Suppose that your mu is split into function of x and function of t. So it's a simple case. Okay. And you are given the spectral density of this random fluctuation. Write your effective parameters in terms of this spectral density.
We did this. In the paper we did this. We
It should be
consider separately this
explicit
case.
formulas.
Yeah, and
With
we-
integral over spectral density.
Yeah,
Okay.
yeah, we did this.
But what information on U0 do you have? U0, phys U0, phys
will be
stationary.
again a solution of just heat equation
with some
up to
diffusion
linear
coefficient.
shift. Yeah, so it's A effective constant matrix which is positive, symmetric, positive, definite. So up to a linear change of variable, it will be just heat equation, solution of heat equation. It's always the profile of U0 is basically always the same.
This theorem is existing in the case of just not operator of a kernel, but just a diffusion operator. It's existing, this theorem.
Sorry, say it again.
So if you replace your A by just some diffusion operator. So here you have A, which is a
diffusion
kernel.
operator, yeah?
No, from the beginning. From the
the
beginning,
beginning.
you have some kernel, but
Yeah, and diffusion operator.
yes.
For diffusion operator, in order to have this picture, we should add first order terms. Because in case of diffusion, even if matrix A is non-symmetric, the drift will be zero, if it's pure diffusion.
Yes.
I mean, if we have the operator divergence A gradient and A is not symmetric, in the limit we will still have pure diffusion, no drift. Because for adjoint operator, the kernel is still a constant. But if we add first order terms, let's say the diffusion part plus P of x gradient U, then the picture will be exactly like here. But strangely, in diffusion case, it's much easier because there is a very good machinery. There's the Georgia theorem, Aronson estimates, all these things. Here, we have nothing like this. So everything, we had to do everything by hands because there is no good results like for diffusion.
Okay, and here your process mu should be uniformly in time elliptic, right?
Right. People, when there is some generation, for instance, there is a recent paper by Chen, Kumagai, and Wang. They studied the case when there is more, they studied slightly different operator, which is with a kernel which is not integrable, more like linear operator. But they studied the case when,
No,
yeah.
without.
When there might be a degeneration, and I believe what they did can be also extended to this case. It's another direction, in a sense, what kind of degeneration we can.
And then you will get a kind of sorry. No, speed. Yes, also no question. There is no question. Any more questions? Thank you again.
У нас есть формула добычи той сигмы, есть формула явная, да? В этой задаче. Явная формула добычи той сигмы имеется, да?
Да, конечно, это надо взять что? Надо взять этот GT и написать интеграл, как обычно. GT, это же матричная, G от нуля.
Надо переписать.
Мат ожидания.
Через спектр.
Да, вот.
Конечно.
Это обычная история, когда стационарный интеграл от стационарного процесса берется. Если свойства перемешивания хорошие, то это самое, эффективная ковариация вот так пишется всегда.
Да, диффузия получается невыраженная, да? Вот.
Диффузия получается, вообще говоря, невырожденная, да.
Ну да, соответственно, если мю вырождается, то,
Она может и вырождаться. То есть, представим себе, что у нас по каким-то направлениям, там, легко, если она от Т вообще не зависит, то предел детерминированный, то есть там вырождения могут быть по части, но в случае общего положения она не вырождена.
ну да, если логическое, наверное, здесь примешивание сильно. Спасибо.
Очень симпатично.
Мало написал, что он извиняется, что не пришел, и я привет. Мало вам передал привет. Очень приятно.
мало времени.